Hello students, we are now going to study the oligosaccharides and polysaccharides. In my previous class, I have taught you how oligosaccharides can be formed, what are the oligosaccharides and how they can be formed by joining 2 to 7 numbers of monosaccharides, glucose units or mannose unit or galactose or a combination of all those things can be made to produce the oligosaccharides. Oligosaccharides are mostly found in nature either attached to a glycoconjugate. Most of the time they are found being attached to a glycoconjugate. That means either a proteoglycan or a glycoprotein. We will come to that later on, what are they. But we find mostly oligosaccharides in association with them. Besides, we will also find freely we will find several disaccharides, a type of oligosaccharide where only 2 monosaccharide units are joined. We will find them plentifully in the nature. Very common of them is the sucrose, the sugar which we take as a sweetener in our day-to-day life. The cane sugar which is found in the sugar cane juice, we find them, then we crystallize them to produce the table sugar. So we begin with these disaccharides. We practically begin with the disaccharides. So I wrote here a chart of these commonly occurring disaccharides. These are maltose, isomaltose, cellobiose, gensiobiose, lactose, sucrose and trehalose. They are found in nature. They are found in the nature as disaccharides. They are found in nature as disaccharides, means freely. Besides, they may remain associated with any glycoconjugate or something like that. So let us see how this maltose is formed. They are formed by joining 2 glucose units. I have already shown in the previous class how 2 monosaccharides can be joined. Let me draw once again. Say this is one glucose. Say this is one glucose. So this is CH2OH, HOH. So this is one alpha D glucopyranose. This is one alpha D glucopyranose. I draw one more. This is another alpha D glucopyranose. Though these 2 alpha D glucopyranose, they are these 2 alcoholic groups, this OH and OH, they will react and they will produce one glycosidic bond. I have told you what are the glycosidic bonds. So from here we will find, and as I have already explained how we will give this glycosidic bond. Now this will be alpha 1,4 glycosidic bond. Bond or linkage. Linkage word is also very commonly used, very often used word. This bond sometimes is misleading. This term bond sometimes it is misleading. We can use this linkage, but all the way the meaning is same. So we will find why we call this alpha 1,4. This first one, whose anomeric carbon atom is used, the monosaccharide unit whose anomeric carbon atom is used in production of the glycosidic bond, we have to check whether it is in alpha configuration or in beta configuration. If it is in alpha configuration, then we will put alpha here. So this alpha indicates this first one is in the alpha form. Then alpha configuration. Then its first carbon atom is being used and it links to 4th carbon atom fourth carbon atom of the second one. So as a result, we find we have this alpha 1,4 glycosidic bond. So this is what your maltose is. This is what maltose. Similarly, we have isomaltose. In case of isomaltose, it will be alpha 1,6. Alpha 1,6 means, say, this is instead of drawing all the substituent, I am just showing here. Both are alpha D glucopyranose. Well, both of them are alpha D glucopyranose. Now this is the first carbon atom hydroxyl group, and this is the sixth carbon atom hydroxyl group of the second one. This one is in the second one, this is the CH2OH group. This is the sixth carbon atom. So this hydroxyl group and this hydroxyl group, they will react, and we will find it like this. This is the carbon CH2, and this is so this is your alpha 1,6 glycosidic bond. So now this becomes your what? Isomaltose. Now when we go for this cellobiose, we will have the same glucose units. Glucose units are same, but that will be beta 1,4. Now this beta 1,4 is different from the alpha 1,4. So let me draw it here. Just I will make it beta. This also I make beta. So in case of beta, if you recall, on this plane of the ring, on which side CH2OH is there, and the same side hydroxyl group will be there. When both of them are on the same side, we call it beta form. And if they are in the opposite side, we call it alpha form. I have repeatedly told it. So now, these two hydroxyl group, we will be now seeing that they would be reacting, and an acetal will be formed. So what will be after their removal, what it will be? It will be like, it is easy to write it like this. It is a bit narrow. So we will have this structure. So beta 1,4, it will be like this. Here is the glucose, remaining part of the glucose. Here the remaining part of the glucose. So this is hydrogen, this is hydrogen. So this is your beta 1,4 glycosidic linkage. So this makes the cellobiose. Similarly, gensiobiose, this will be beta 1,6. You can easily make beta 1,6. It is here, it is alpha 1,6. We can make it beta 1,6. In beta 1,6, what will happen? It will be, hydrogen will be like this, and this is now beta 1,6. Beta 1,6 glycosidic linkage, this will be gensiobiose. So these four, and another one is trehalose. You bring trehalose to this list. Remove, just you, without this you just see. So now come to the trehalose. In trehalose, again two glucose units are there. There are two glucoses, and they are joined with alpha 1,1. That is interesting because this is also anomeric carbon atom. This is also anomeric carbon atom. Both of them are anomeric carbon atom. So how they will be formed? Let me draw it here. This is HOH, and the other one will also be, we can say another one. Say for instance, we draw it here. So we will find this is the one of this and this is one of this. So both of them will be joined. Both of them, and both are in alpha form. So both of them will be joined. We can put it like this. We can put it like this. Actually, if we are using Haworth projection formula, you are not much acquainted with this. We can reverse this structure of this, just we can write it in a reverse manner. So such that we can reverse it upside down and such that the right side becomes the left side. If we write in that manner, then we can draw this very easily, but it may be a bit confusing for you which side which has gone. So I am just avoiding that. So this is your trehalose. So here we found 5 disaccharides. Here we have listed 5 disaccharides which are made out of glucoses only. They are combination of 2 glucoses using alpha 1,4 glycosidic linkage, beta 1,4 glycosidic linkage, alpha 1,6 glycosidic linkage, alpha beta 1,6 glycosidic linkage, as well as the alpha 1,1 glycosidic linkage. So all of them are interesting molecule. Let us see where we find them. This first one, maltose, we find as a digestive product. When the starch is getting digested inside our stomach, we used to find them in our alimentary canal at various sites. We will find them plentifully. Whenever the starch is digested, it produces usually maltose, maltotriose and limidextrin. These are the things which we used to get. So isomaltose, also the partial digestion of the amylopectin will produce the same thing. Then cellobiose, they are the repeating unit of the cellulose, about which we are going to study, the cellulose, the polysaccharide. Then gensiobiose, we find it mostly in several antigens, as well as we will find them in saffron. You know that saffron is a the stamen of a flower. We find it in the Kashmir, and they are used as coloring agent with a very sweet flavor, color as well as flavor, saffron. And we believe that it has lots of medicinal value. So next one is the trehalose. Trehalose is a very unique molecule in the sense that both of its anomeric hydroxyl group are being consumed, means being joined together. As a result, they do not have any reducing capacity. I will come to that. The remaining 4 are reducing sugars. Reducing sugars means they can reduce the copper solution. They can reduce the copper solution, but this one cannot. This cannot do that because its anomeric carbon atom is no more working. So we do not, this is a non-reducing sugar. In fact, we use Benedict solution in the laboratory, to test presence of reducing sugar and non-reducing sugar. So if we are having the reducing sugar, then Benedict solution will Benedict solution will be turned to brick red precipitate, from the orange or say green to brick red. That depends upon how much reducing sugar is present in your solution. So now, but if we are using trehalose, the Benedict solution will remain clear blue color. It will remain as clear blue color even if we boil it for very long time. Then we come to lactose and sucrose. In case of lactose, we find galactose and glucose. And in sucrose, we find glucose and fructose. Let me draw their structure. I am giving much stress on structure as you mark, because in biochemistry structure is very, very important. We have to understand this structure because structures can only if we are master in structure, it will bring a kind of confidence with us, and without understanding the structure, you cannot understand biochemistry. So in galactose, we draw galactose. In galactose, hydroxyl group will be at the top at the third carbon atom as well as the fourth one. In both the cases, it will be then CH2, OH and H. Then here it will be oxygen. It will be beta galactose, and you just mark it. It is beta. So OH will be here, H will be here. Then glucose. Glucose is also beta. Here glucose is also beta. So this is your beta D galactopyranose. Galactopyranose. And this is beta D glucopyranose. This is beta D glucopyranose. So what will happen? We will have a beta 1,4 linkage. So these are the things. We have to replace it with an ether linkage, the glycosidic linkage. So this is the lactose. Lactose we find as the milk sugar. They are the sugar of the milk, and this is very much essential in case of the newborn babies up to a quite long time, because they have this galactose, and galactose is important in development of the brain. There are some people who cannot tolerate this lactose, that is called lactose intolerance, and in case of lactose intolerant babies, they may become mentally retarded. So next one is the sucrose, commonest. The commonest disaccharide. We always use them as the sweetener. So here what happens? There is glucose and fructose. We will have the glucose. So glucose, it is alpha 1, 2. This glucose is alpha D glucopyranose. So here it is OH and here it is H. Now fructose we can draw here. Fructose will have the furanose structure, fructofuranose. This fructose will be beta D fructofuranose. Beta D fructofuranose. So here it will be OH, CH2OH in beta form, OH, H, OH, CH2OH and H. We can write it this side. So this is our fructofuranose, and the reaction will be between these two hydroxyl group. Reaction will take place between these two hydroxyl group. So we will have this one. One water molecule is always getting removed. So this is our sucrose, found in the cane sugar. It is found in the cane sugar. So I think that is all about the all kinds of disaccharides we have discussed, and as I have told that most of the other oligosaccharides are actually found in the they are the conjugant in case of the glycoconjugates. All kinds of glycoconjugates we find them plentifully. Plentifully means plentifully. So next we go for polysaccharide. When we say polysaccharide, we mean more than 30 monosaccharides are joined together. more than 30 monosaccharides are joined together. How do we express it? We speak it like this. When those are polysaccharides which upon complete hydrolysis will produce above 30 monosaccharide units. On hydrolysis yields more than 30 monosaccharides. That is what we call the polysaccharides. Now, polysaccharides, we can classify them like this. We can classify them into homopolysaccharides and heteropolysaccharide. Say polysaccharide, homopolysaccharide. When we say homopolysaccharide, what we mean? And this is heteropolysaccharide. When we say homopolysaccharide, what we mean? Same kind of monosaccharide. Same kind of monosaccharides. When we hydrolyze them, only one kind of monosaccharide will be found. But here when we hydrolyze them, more than one kind. Monosaccharide will be found. So that is what we mean when we say this thing. So now this homopolysaccharide are basically, we can divide them into two further categories. They are structural and storage. And when it is heteropolysaccharide, we can say they are protective and structural. They are never used for storage. When we say storage, what actually we mean? When we say storage, what actually we mean is they will store monosaccharides for future use. They will store monosaccharide for future use. When we say structural, they will be producing a structure in the body of either bacteria or plant or animal or whatsoever organism it may be, or a fungi, whatsoever it may be. So then we will just we'll just study some candidate polysaccharides. We will just check some candidate polysaccharides, and we will begin with homopolysaccharide. Begin with homopolysaccharide. When we say heteropolysaccharide, in fact, these heteropolysaccharides are very often part of the glycoconjugate, because do not forget that there is a class of carbohydrate which we call glycoconjugates. We will come to that later on. First, we will discuss about the cellulose. We will discuss about cellulose. So, cellulose is the homopolysaccharide. Function is structural. Homopolysaccharide, and it is structural. Homopolysaccharide of what? Of beta glucose. Beta glucose means beta D glucopyranose, beta glucose, and they are joined using beta 1,4 linkage. How many? Over 50, more than 50,000 glucose residues. More than 50,000 glucose residues are joined together to produce the cellulose. Now, interestingly, what happens here? the molecules are flipped 180 degree alternately. Means if one glucose is like this, another glucose is like this. So they are always flipped like this. As a result, what happens, if they are on the one side, then they will be like this, an angle will be produced among them. But since they are rotated 180 degree, they are flipped 180 degree. So what we find is that they can make a straight chain. They make a linear chain. They make a linear. So this is what we find, it is linear. Means unbranched. It is unbranched. So these cellulose molecules, what will happen? They can lie like this. Several of them can lie together, such that a bundle of cellulose molecules can produce a cellulose microfibril, and they gradually make bundles, then bundles, then bundles, and they can provide mechanical strength to the structure. Very well, very good mechanical strength to the structure. So now, so where do we find them? They are found in the cell wall of the plants. Cell wall of the plants. Now you can mark, cell wall of the plant means they are, how much they are considered the most abundant biomolecule found in the living world. Most abundant, highest quantity of them are being present. You just see, this cellulose you find almost at many of your day-to-day usable things. If you have a cotton pant and shirt, they are made up of cellulose. Just imagine, cellulose is made up of glucose. Means your shirt and pant are made with glucose only, and that is almost 95% pure glucose. The same glucose which you drink as Glucon-D, in the same Glucon-D which you drink, the same Glucon-D make your shirt, pant, bench, chair, your paper on which you are writing, all these things are made up of pure glucose. You just can imagine what is this biochemistry. The biochemistry of all these things you can just imagine. Not only that, the dynamite which we make to blast the things, they are also made of this glucose, cellulose. So next we think of another structural homopolysaccharide, of course, structural homopolysaccharide, that is chitin. Second candidate is chitin. This is N-acetyl D-glucosamine, homopolymer of N-acetyl beta D glucosamine. This is also joined by beta 1,4 glycosidic linkase. Beta 1,4 glycosidic linkase. So now, if we draw this structure, it will be something like this. I have already shown you the structure of the glucosamine. So it is a beta, so means will be like this. Beta, the structure will be like this. So that shows the continuity. This side also we will have the continuity. This is N-acetyl D-glucosamine. So this is just repeating unit, and it continues like that. Here beta 1,4 linkase, this is beta 1,4 linkase. These two are the repeating unit, beta 1,4 glycosidic linkase. Now, these chitin also flipped. Here the monosaccharide units are also flipped 180 degree alternatively. As a result, we get a straight chain. And where do we find it? we find it in two very prominent places. One is cell wall of fungi. Second one we find in the exoskeleton of arthropoda. Exoskeleton of arthropoda. So they can be present as alpha chitin or beta chitin or delta chitin. In alpha chitin chains are parallel. Chains are parallel. In beta chitin chains are anti-parallel. In delta, we will find chains there are two parallel sheets sandwich an anti-parallel sheet. What does it mean? A sheet is made up of bundles of chitin fibers. So one chitin layer will be made up of parallel fibers, then another parallel fibers, then in between these two there will be another layer where there will be parallel, next anti-parallel. Means one is from this side to that side, and means say here it is 1 and here it is 4. So anti-parallel means this side it will be just you flip it like this, then it becomes anti-parallel. So like this we will have it. Thank you. We will again resume it.